Good morning, students. I am Professor N.V.S.N. Sharma from NIT Warangal. In today's class, we are going to discuss a new type of radar called continuous wave radar or Doppler radar. As we see cars moving with petrol as well as diesel, radars also are of two types. One is a pulsed radar and the other one is a CW radar. In the cars, we see the main purpose is served by both types of fuels, but the cars will have a different structure depending on the fuel used, and both the types have their own advantages and disadvantages. Similarly, in the radars also, we have two types. One is a pulsed radar, which we discussed already, and the other one is the continuous wave radar, or in short we call it as CW radar. In this class, we are going to see the details about this CW radar and also a comparison between the two types, the CW radar and the pulse radar. So let us see now what are the objectives of this class. The objectives are to understand the differences between pulsed radar and CW radar, what is required in a CW radar to see a target. That means to detect that a target is present in the vicinity, and understand what exactly is this Doppler shift means and how to find this Doppler shift, how to calculate the combined speed between target and the radar. That means when the radar is moving and the target is also moving, how do we find the distance and other details. Then we are going to find out what are the components of a basic CW radar system and understand their operations and characteristics. Finally, let us see how we can determine the range of a target using a CW radar. While discussing all these things, we also come across the applications of CW radar and its modified form, which we are going to see as frequency modulated continuous wave radar, or in short FMCW radar also. So finally, the crux of this is going to see what are the two basic types of radars. One is a pulsed radar, wherein a pulse is being used for transmission of the signals and identifying the coordinates of the target with the return signal of this pulse. The second one is the CW radar, wherein continuously we are going to send a particular type of waveform towards the target. The reflection from the target is going to be mixed with the transmitted signal, and from that difference we are going to find out the details of the target. So here let us see the basic difference. A pulsed radar is typically used to detect targets, determine the range and bearing, or in other words azimuth of the target. These radars are generally having quite high power. They are quite complex and also expensive. Whereas the one which we are going to discuss, that is the continuous wave radars, typically determine target velocity and can achieve considerable ranges without high peak power. So here you can see the point of interest will be velocity first, whereas in the case of pulsed radar, the main interest will be on the range. Here in CW radar, low power transmission is sufficient to get the details, and hence they are less costly. So let us understand the physics of this CW radar. The entire CW radar depends on a particular effect which we studied in our high school, that is Doppler effect. Let us understand the Doppler effect in the light of this CW radar operation. Doppler effect is the change in the frequency that occurs when a source and a target are in relative motion. In short, what we can say is, when you stand by the side of a railway track and if a train moves, then we see that the frequency of the received signal is going to change. This is what we studied in our sound subject long ago. Here we are seeing that the source is moving, that is the train, and you are the receiver who is stationary. But it is not necessary that the receiver must be stationary and the source must be moving. The converse can also be the case. Again, in that case also, we are going to see that the Doppler shift takes place. So, putting these two things together, we can say that either the source or the receiver or both are in moving, the received signal is going to have a different frequency compared to the transmitted signal. The picture in this slide indicates that the transmitted signal from the radar is going to have one frequency. The received signal from the target is going to have a different frequency. By looking at the diagram, one can easily come to know about this. So, the change in the frequency of the received signal is known as the Doppler frequency shift, or in short, Doppler shift. Why does it happen? Why do the frequencies are different? In this slide, you can see the picture wherein the transmitted signals are indicated by A and B, which are separated by a wavelength lambda t. So as they move close towards the target, we see that the target is going to scatter them and return towards the source. When the source is going to receive A at a particular time, but the B will arrive earlier than that because the target has approached the radar. So the return signal will be having phase lead compared to the earlier return signal. So this phase lead over the time, or the rate of change of this phase lead, is going to give rise to the Doppler frequency shift. So here we can see in this equation shown, the lambda r, or the received signal wavelength, is going to be different from the transmitted signal wavelength by an amount of 2Vt. What is this 2Vt? Let us see in the next slide. When the vehicle in which the radar is kept is moving towards the target and the target vehicle is also approaching it, you can see the waveforms are getting compacted, are getting close by, and hence this closeness is coming to the calculation by 2Vtt as indicated in the figure, and hence the received signal wavelength is going to be less, or the frequency of the received signal is going to be higher than the transmitted signal frequency, because the radar and the target vehicle are approaching each other. If they are receding, then the received signal frequency is going to be lower. Pictorially, the changes are shown here. In diagram B, you can see that the first waveform that's coming towards the target is A. Then at a wavelength of lambda t, you have another waveform of B. Another waveform is at C. As the target approaches towards the radar, you can see the next one is hit at earlier than A location or A dashed. Similarly, B dashed and C dashed, and hence they are having a phase lead corresponding to the velocity and the time. Now, when do we get this Doppler shift? In this slide, you can see the pictures that the target velocity can be determined as long as the target is moving perpendicular to the antenna beam. If the target is moving in the other direction, that is perpendicular to the normal to the antenna beam, then the cos theta between these two things is 0, and hence you cannot determine the target velocity. Accordingly, you can also see if there is any angle between the line of sight of the antenna beam and the target velocity, then cos theta of that will come into picture in the calculation of the velocity. So putting these things, we can see now the velocity of the target with reference to the antenna beam is given by the equation as shown in the slide. Here we can see the characteristics required for a CW radar. Normally a CW radar is used to measure the speed of the incoming target, and in the picture shown you can see various blocks of this CW radar. One is an antenna, the other one is what is the speed of the incoming target displayed, and this can be made on a portable device. So here you can see the characteristics are like this. The duty cycle is going to be 1 because we are going to transmit the signal continuously, unlike in a pulsed radar. In a pulsed radar, we are just transmitting for a short duration and waiting for the echo for the off part of the duty cycle. Now there is no off part here, continuously the transmitter will be on, and hence the duty cycle is going to be 1, and the peak power is same as the average power. By this, what we are going to achieve is the high signal to noise ratio in the received signal. And as the target is always illuminated and we are getting continuously the return signals, the Rmin is 0. That is, the minimum distance with which you can measure the target is going to be 0. Now let us see the other side of this CW radar. In the normal pulsed radar, we are sending or receiving at any given time, and hence we have the advantage of using a single antenna, and using a duplexer we can connect the antenna once with the transmitter to transmit the signal and then switch over to the receiver to receive the signals from the targets and process them further. So a single antenna is sufficient in the case of a pulsed radar. But in the present case of CW radar, we are continuously sending the signals and continuously receiving the signals, and hence we require two separate antennas. This is the flip side of a CW radar system. And the basic disadvantage of a CW radar is that it cannot measure the range. It means velocity can be measured directly and range cannot be measured. Whereas in the case of a pulsed radar, range can be measured directly and the velocity will be derived from the range. So let us understand the basic operation of a CW radar with some diagrams and equations. Now, so the fundamental condition for the operation of a CW radar is that either the radar or the target must be moving. If both are moving also is acceptable. What we are going to measure is the received signal frequency shift. That is, we compare the transmitted signal with the received signal and see the difference between the two frequencies. Hence, in the receiver, the frequency measurement is the key. With the accuracy of this frequency measurement, we get an accurate data of velocity of the target. And the Doppler shift is directly proportional to the range of the target and the wavelength of operation. So here the Doppler shift is now given in terms of the velocity and the wavelength as 2s by lambda. The s is defined as the speed in the line of sight. That means along the direction of the radar, what is the velocity of the target. And if the radar is also moving in a different direction, then we have the speed of the radar in the line of sight and the speed of the target in the line of sight adding together will give us the average of the velocity along the line of sight, and this must be used in the calculation of the Doppler shift. So let us consolidate all these things that are developed so far. The first thing is that a CW radar employs continual radar transmission. It has separate transmit and receive antennas. For the basic operation, it relies on Doppler frequency shift, or in short, Doppler shift. So here again you can see the line of sight of the radar, which is kept away from the road, is going to be different when the target is approaching the radar. That means the radar is kept on the side of the road, and when the car is moving, then the line of sight, the range and separation of the radar from the main road are indicated in the diagram shown, and we have the angles also taken care about this. Taking all these things into account, finally the velocity will be displayed on a display unit in terms of either miles per hour or kilometers per hour. When the target as well as radar are moving, the diagram here shows to calculate the velocity in the line of sight. This velocity is the relative velocity between the target and the radar system. So taking these things, we can also find the bearing of the target in terms of the radar. That means the angular location. So here the relative bearing is calculated from true bearing minus the heading of the radar system. In certain cases, we require reciprocal bearing. So a reciprocal bearing is calculated taking the true bearing plus or minus 180 degrees of this calculated value. Then this is essential when you are looking from a ship towards an incoming aircraft or an outgoing aircraft, and this plays a very important role in those calculations. We shall see the block diagram of a CW radar system. So from our knowledge so far, we are to send a continuous signal from a transmitting antenna. So the transmitting antenna is connected with a high frequency oscillator which generates this continuous wave signals. The transmitted signal will be towards the target. The target is going to reflect them. Then the received signal from the target, or what we normally call as echo, is going to be given to the receiver block. The first subsystem in the receiver is going to be a mixer, because we are interested to find out the frequency difference of the received signal from the transmitted signal. The mixer will have two inputs. One is the sample of the transmitted signal, and the other is the received signal. The mixer output is going to be the difference frequency of the two inputs. That means it contains the Doppler frequency shift. That will be amplified, and we are going to use a discriminator to find out what is the value of this. And using the simple mathematics, we can find out what is the velocity from this. The velocity will be displayed on an indicator. So the main blocks are as shown in the slide: a transmitter, a transmitting antenna, a receiver which contains a mixer, an amplifier, a discriminator and an indicator. This receiver block is attached with a receiving antenna. So this is the simplest one which we can imagine from our theory so far. But in practice, we need to have many more additional things to take care of the unwanted effects. So we are going to see them at a later stage. And all these blocks are having the power requirement. So a power supply is separately shown in the next block diagram, and the RF oscillator what we are going to use will be a simple sine wave generator of hundreds of megahertz or even gigahertz. So at hundreds of megahertz, we may consider a low power oscillator with a high power amplifier, or a direct high power oscillator like a magnetron or similar vacuum tube devices. The antenna is going to be a normal parabolic dish if it is going to be a microwave frequency operation. If it is a low frequency operation, then we may consider a horn antenna or similar things. But definitely it's going to have some sort of directionality to see that the power is concentrated towards the target expected direction. Similarly, the receiving antenna is also going to be a parabolic dish or a horn antenna or similar directional antenna. Here, the received signal is normally very low, and to have a good output signal from the receiving system, the effective aperture must be large. So in that sense, a directional antenna is preferred in the receiving case also. The received signal is going to be mixed in a mixer, and the mixer is the crucial part which mixes the input signal from the receiver with the sampled signal of the transmitter and gives out the Doppler frequency shift. So we need to be very careful because mixer is normally a noisy process. The discriminator is used to find out the frequency shift. So this discriminator must have a uniform input, and it must be able to identify the frequency very accurately. The frequency calculation is done by using a counter at low frequencies, but at high frequencies we use different techniques. The output of the discriminator is calibrated in terms of velocity, because the velocity is the final parameter of interest for the user, like a policeman standing on the roadside for finding out the speeding vehicles. So the velocity will be calculated from the frequency shift using the simple formula like 2s by lambda, and from that the velocity will be indicated either on an analog meter or on a digital meter in terms of miles per hour or kilometers per hour. The discriminator basically eliminates the stationary targets from the moving targets. the stationary targets will give rise to the same frequency as the transmitter frequency, and hence the Doppler frequency shift is going to be 0. But for moving targets only, there is going to be a finite value. So the discriminator must avoid the DC values of the incoming signal. So this is taken care by using a proper capacitor in the circuit. The indicator is going to be a 3.5 digit or a 4.5 digit type of digital indicator with sufficient accuracy to get the kilometers per hour indication normally. The power supply is basically to power up all the blocks of the transmitter as well as the receiver, and sometimes we may use a portable power supply also, because these radars are going to be used on the field. The Doppler amplifier shown in the block diagram is the crucial part of this entire receiver. It is supposed to eliminate the echoes from the stationary targets. That means it should have a response above 0 frequency, that is DC. But how much above is the crucial design aspect of this, because if you are moving much away from 0 means that you are not going to detect the targets which are moving slow. The slow moving targets will be giving rise to low frequency shift in the received signal, and if the amplifier is not able to amplify them, they cannot be detected. So at the working site, we should have an idea about how much fast moving target must be detected, how much slow moving target must be detected. Taking these two things into frequency domain, that means what will be the corresponding Doppler shift of these two cases, we should identify the frequency response required for the Doppler amplifier as shown in the diagram here. So putting this in a statement, we see that the Doppler response must be low enough to pass the smallest Doppler frequency expected from a very slow moving target, and also the high frequency cutoff must be sufficient to see that the fast moving targets giving rise to high Doppler shifts are also amplified properly. Let us see something about the indicator. The indicator must be a pair of earphones or a frequency meter. A pair of earphones was the normal practice for a long time. Why? The earphones are better selective band pass filters. They are more effective if the target speed is very high or very low compared to an indicator. And different tones can be used to indicate different ranges of velocities. So with this advantage, the operator also will be quite alert all the time and will be able to identify the incoming target much ahead. The transmitter leakage power is very much used in the mixer to compare it with the received signal. But here utmost care must be exercised to see that the leakage power is not above the danger level of the receiver. It should not damage the receiver. The amount of transmitter noise due to hum, microphones, stray pickup and instability must also be small, because they are directly entering into the receiver through the mixer and create the trouble of the target is at a different velocity and other things. Can we avoid using two antennas? Can we use a single antenna? The answer is yes, but with the low accuracy of the received signals. The following question answer session refers to the topic of CW radar.
Sir, is there any way we can measure the velocity of a target moving perpendicular to line of sight?
Is there any way we can measure the velocity of a target moving perpendicular to line of sight? As we have seen the slides, if the target is approaching the radar or moving away in the same line, we can definitely measure the velocity, or if it is moving at an angle, we can still find out the component of this in the perpendicular direction. But if the target is moving tangentially, we cannot measure the velocity using a radar system.
Sir, how do we eliminate the noise generated by mixer in a continuous wave radar system?
How do we eliminate noise generated by a mixture in a CW radar system? As such, the mixer operation is a noisy process, and hence by using a device with low noise and operating it exactly in the square law region, we can see that the noise is minimized, but it cannot be eliminated completely.
Sir, what are the techniques used in the discriminator to calculate the frequency shift at high frequencies?
What are the techniques used in the discriminator to calculate the frequency shift at high frequencies? A discriminator is supposed to give us the frequency of the input signal. So if the frequency of the input signal is very high, in the first stage, we are going to use a frequency divider and reduce the frequency so that we can make an accurate calculation of the zero crossings of the signal and make the measurement more precise. So depending on the input signal frequency, we try to use a chain of 2 or 3 frequency dividers and bring it down to an acceptable value and then measure the frequency. Finally, calibration will be done depending on the number of reductions that are done previously.
Sir, what are the different IFs that are used?
4. What are the usual IFs used? The IF is chosen so that the image frequency of the signal is definitely out of range of the operation. That is a thumb rule used in communication engineering. Here also, in the case of radar systems, we use the same principle. So for a 10 gigahertz radar, we normally choose the IF to be around 1 gigahertz. That means 1/10 of the RF signal input will be the IF chosen. In general, it will be in the range of 1/3 or 1/5 depending on the application. Yeah.
Sir, is range resolution of FMCW better than pulse radar?
Thank you. Yeah. Is range resolution of FMCW better than pulse radar? It is when considering range resolution that the FMCW radar tends to come out on top. Without a lot of processing, the best that a pulse radar can deliver is determined by the pulse width. For reasons beyond the scope of this class, it corresponds to a return of approximately twice that pulse width. That means a 100 nanosecond pulse will give a range resolution of about 30 meters. The resolution of a FMCW radar has no lower theoretical limit. Rather, the resolution comes from the engineering implementation and practically could be as low as 5 meters or so. That also makes the FMCW radar less susceptible to sea clutter because it is less likely to join the waves together in a single mass. Thank you.